Welcome to the Global WarWatch Network. Today, we're exploring a monumental shift, really, in space exploration. Imagine NASA's deep space missions, operating for centuries, not just decades. NASA's deep space missions are about to get a major upgrade. Forget plutonium scientists are turning to a fuel that could last over 400 years. Why the sudden switch, and what does it mean for the future of space exploration? Let's uncover this.
Yeah, this is a really crucial conversation. It's about how we power our journey out there into the cosmos
Yeah.
and the new science that's making these truly long-duration missions, well, potentially a reality. We're looking at various sources here, NASA updates, detailed lab reports, trying to bring you the full picture.
Right. So to really get why this new fuel is causing such excitement, we probably need to start with the old workhorse, right? Plutonium-238. What exactly are these nuclear batteries, and why have they been so essential, especially way out there where sunlight doesn't help?
Well, for those really long-term, long-distance missions, think, beyond Mars or places that are always dark and cold, solar panels just aren't practical, not enough light, basically. That's where radioisotope power systems, RPS, come in. They're essentially uh, power sources that generate electricity from heat. And that heat comes from the natural radioactive decay of a specific isotope. Think of them as incredibly resilient power packs. No refueling needed, no sunlight, just steady power.
Okay, like tiny constant heaters providing electricity.
Exactly. Indispensable for deep space.
And plutonium-238, or Pu-238, specifically plutonium oxide, that's been the go-to for decades, hasn't it? We're talking about huge missions, the Voyager's still going, New Horizons past Pluto, Curiosity, Perseverance on Mars. I mean, these things redefined our view of the solar system, all thanks to Pu-238. But it does have downsides, limitations.
Oh, absolutely. It's been incredibly reliable, a marvel of engineering, really. But plutonium-238 has a half-life of roughly 88 years, 87.7, 88 years, around.
88 years.
Yeah, which sounds like a long time to us. But in mission terms, it means the power output steadily drops over the decades. So the mission might survive, but it has less and less power to run instruments, transmit data. Mission planners end up having to make really tough choices. Shut this down, limit that. It's a slow fade.
It's a ticking clock, basically.
Precisely. And beyond that, actually producing it has been a huge challenge. The U.S., for example, stopped making it in bulk for nearly 30 years. They only restarted around 2011. They even had to buy supplies from Russia for a while. So getting enough reliably, that's been a constant headache, a real constraint.
Okay, so power decline over time, plus a tricky, sometimes geopolitical supply chain. If those are the issues with plutonium-238, what's this alternative that scientists are getting excited about now?
That would be Americium-241, Am-241. It's an actinide like plutonium gets created when you irradiate uranium in a reactor. But the key thing is it forms naturally as another isotope, plutonium-241, decays within used nuclear fuel.
So it's a byproduct, not something you have to specifically manufacture from scratch in the same way.
Exactly. It's derived from existing processes, which is a potential advantage.
Okay, now here's where it gets really interesting for me. You said P238 has an 88-year half-life. What are we looking at for Americium-241?
Well, Americium-241, it has a half-life of around 430 to 433 years.
430 years.
Yes, it's a massive difference. A genuine game changer for how we think about mission length. It means a power source could theoretically last for centuries, almost 5 times longer than P238. We could power missions far beyond anything we've seriously planned for with current tech. We're talking generational timescales.
That's just incredible, a nearly five-fold increase in lifespan. And what about the supply? You mentioned the issues with Pu-238. Is M241 easier to get hold of? Does it solve those problems?
Well, potentially, yes. That's a major part of the interest. Because it comes from the decay of plutonium-241 in spent fuel, there are actually quite large existing stockpiles. Just in the UK, for example, there are estimates of over 100 tons of separated civil plutonium, and that contains significant amounts of Americium-241.
100 tons, just in the UK.
That's the figure often cited. So it makes Am-241 a potential long-term sustainable source, particularly for Europe. It could offer independence from those existing Pu-238 stockpiles, which are mainly held by the U.S. and Russia.
Right, so it's not just about lasting longer, it's also about strategic independence, using existing resources differently.
Exactly. It taps into a resource stream that's already there, potentially turning a waste management issue into a valuable asset for space exploration.
That adds a whole other dimension, geopolitics and resource management playing into deep space capabilities.
It really does. It opens up possibilities for different players, different collaborations.
Okay, so the fuel lasts incredibly long. and it might be more accessible, but how do you actually turn that long-lasting heat into electricity on the spacecraft? Is the tech changing too?
Yes, and that's another key part of the story. One really promising approach uses something called free piston Stirling converters. These are different from the older RTGs radioisotope thermoelectric generators, which use thermocouples. Thermocouples are simple, very reliable, but not very efficient, maybe 5–7%.
Right, the solid-state ones.
Stirling converters are more like engines, but highly advanced. They use pistons that essentially float magnetically or gas bearings within the engine. No crankshafts, very little physical contact or wear.
Floating pistons in space.
Yeah, it makes them much more efficient, potentially over 20%, maybe even 25% efficient, and very durable, especially in microgravity. In fact, one of these converters at NASA's Glenn Research Center ran continuously for 14 years without any maintenance.
14 years nonstop.
14 years. That alone meets the baseline requirements for many outer planet missions. It shows the converter technology itself is incredibly robust.
That's impressive durability for the converter. But are we actually testing these with Americium-241 or simulations of it?
We're getting there. In January 2025, NASA Glenn actually partnered with the University of Leicester in the UK. They tested a Stirling generator test bed, but powered by electrically heated simulators designed to mimic AM241's heat output precisely.
Ah, simulators. So not the real fuel yet, but matching its heat profile.
Exactly. It's a crucial step to validate the performance, the efficiency, make sure the system works as expected with that specific heat source characteristic. And they met their targets. Alongside this, the UK's National Nuclear Laboratory, UKNNL, they've been working with the European Space Agency, ESA, on this since way back in 2009. They've actually managed to recover gram quantities of high-purity AM241, so progress is being made on the fuel processing side, too.
Okay, so NASA, Leicester, UKNNL, ESA. This sounds like a really strong international collaboration pushing this forward.
It definitely is, which is encouraging, but it also hints at the complexity. This isn't simple.
Right, because while the potential benefits are huge, that 400-year lifespan, the availability, it can't be all smooth sailing. What are the major hurdles, the challenges?
There are significant ones. A key difference is radiation type. Pu-238 is mainly an alpha emitter. Alpha particles are easy to shield paper, skin stops them. M241, however, emits a lot more gamma radiation, and gamma rays are highly penetrating. They need heavy shielding, like lead or thick concrete.
So the handling is completely different.
Completely. Facilities built for Pu-238, often using things like Lexan plastic or water for neutron shielding, just aren't suitable for AM241's gamma rays. You'd need major, very expensive retrofits. Think leaded glass windows, reinforced shielding walls. The cost estimates are significant, potentially millions per glove box unit needed for processing.
Wow. So the infrastructure needed is a massive cost barrier right there. What about the fuel itself on the spacecraft?
Two main issues there: weight and fabrication. AM241 has a lower specific power than Q238. Basically, you need more americium by mass to get the same amount of heat and thus the same electrical power.
How much more?
Significantly more. For a standard power unit like the GPHF RTG design, you might need, say, 300 pounds of AM241 fuel compared to maybe 60 pounds of Pu-238 fuel to get the same electrical output.
5 times the fuel mass.
Roughly, yes. And for space missions, weight is everything. Every extra pound costs a fortune to launch and impacts mission design, trajectory, everything.
That forces some really hard trade-offs. More fuel means less science gear or a much bigger, more expensive rocket.
Exactly. Or maybe slower travel times. It complicates the mission design considerably.
And you mentioned fabrication, making the actual fuel pellets?
Yes, the chemistry is trickier. Americium oxide is apparently harder to work with than plutonium oxide. Making robust, stable ceramic fuel pellets, which are critical for safety, especially during launch or if there's an accident, is more difficult. There were early tests done in Germany that apparently showed some cracking in small AM241 oxide pellets. That's a serious concern that needs to be fully understood and solved.
Okay, so infrastructure costs, the weight penalty, and challenges making safe, reliable fuel pellets. That's quite a list. What kind of timeline are we looking at for this to actually be ready for flight, given all these hurdles?
The estimates, particularly from the ESA-led side, suggest it's likely at least 10 to 12 years away. And that's just to get to the point of having the raw material or fully fueled power systems potentially available. There are still substantial risks understanding exactly how americium oxide behaves in accident scenarios, perfecting that ceramic manufacturing. These are not trivial problems. And then you have the whole launch safety approval process, especially in the U.S. That involves detailed environmental impact statements, safety analysis reports. That process alone typically takes 4 or 5 years.
And the European testing doesn't quite match U.S.
It
requirements.
could add even more time, requiring further tests or analysis. It's a complex technological and regulatory path.
It certainly sounds complex, but let's imagine they overcome these challenges. If Americium-241 lives up to this promise, what does it unlock for space exploration? What becomes possible?
It enables truly generational missions. I mean, think about it. A probe launched in, say, 2050 could theoretically still be operated and still sending data back in the year 2480. That longevity allows for completely unprecedented science. Continuous monitoring of outer planet systems for centuries, exploring the really distant, dark, dusty corners of the solar system with sustained power. Imagine, landing seismometers on an icy moon like Europa and listening for ocean activity not just for a few years, but for centuries. Or sending a probe towards the Oort cloud, the very edge of the solar system, knowing it could still be functional when it gets there generations later. Missions like Dragonfly, the quadcopter planned for Saturn's moon Titan, they're already relying on advanced long-life RPS concepts. AM241 could push that kind of ambition even further.
It really shifts the timescale of exploration entirely, from missions lasting years or decades to missions potentially outlasting entire human lifespans. So for us listening back here on Earth, what's the takeaway? What does this shift mean for our relationship with space?
I think it means we're potentially entering an era where our robotic explorers can become almost permanent fixtures out there, continuously sending back discoveries for generations to follow. This shift to Americium-241 isn't just swapping one fuel for another. It's fundamentally changing how we think about mission duration, maybe even energy independence for space exploration beyond Earth orbit. It forces us to consider the very limits of what we can explore and maybe even asks a bigger question. If our machines can endure for centuries, what kind of long-term, ambitious science do we want them to pursue for humanity?
A profound thought indeed. Planning science not just for our careers, but for our great-grandchildren. That's all the time we have for this exploration of Americium-241 and the future of space power.
Thank you for tuning in. It's certainly a fascinating development to watch.
Please do like, share, and subscribe to Global WarWatch Network. We genuinely love to hear your thoughts on this. Leave them in the comment section below. And you can join the conversation on social media too. All the links you need are right there in the description. Thanks for listening.